Welcome to another episode of Explaining Things in 10 Minutes. Today, we are diving into the fascinating life cycle of stars. Imagine the vast, cold expanse of space. It's not empty. It's teeming with clouds of gas and dust, the building blocks of stars. These clouds, often spanning light years across, are called nebulae, the stellar nurseries of our universe. Within these nebulae, gravity plays a cosmic game of attraction. Particles of gas and dust, drawn together by this invisible force, begin to clump together. As these clumps grow larger, their gravitational pull intensifies, attracting even more particles. This process can take millions of years, a slow, deliberate dance orchestrated by gravity. These dense clumps, now significantly larger than our solar system, continue to contract under their own gravity. As they collapse, the particles within them collide with increasing frequency and ferocity. This generates heat, immense heat, raising the temperature at the core of these contracting clouds. As the temperature at the core of these collapsing clouds reaches millions of degrees Celsius, something incredible happens. The intense heat and pressure cause the hydrogen atoms to move at extraordinary speeds, setting the stage for a cosmic phenomenon. The hydrogen atoms, now colliding at unimaginable speeds, fuse together in a process known as nuclear fusion. This fusion is not just a simple combination, it is a powerful reaction that transforms matter and releases energy. This fusion process, often referred to as the engine of stars, releases an incredible amount of energy. This energy is what powers the star, allowing it to shine brightly in the cosmos. This energy, radiating outward from the core, creates an outward pressure that counteracts the inward pull of gravity. This balance is crucial, as it prevents the star from collapsing under its own weight. This delicate balance between gravity's inward pull and the outward pressure from nuclear fusion marks the birth of a star. It is a moment of cosmic equilibrium, where forces of nature are perfectly aligned. A star is born, a giant luminous ball of plasma, primarily composed of hydrogen and helium, held together by its own gravity. This new star will now begin its life cycle, shining and evolving over millions or even billions of years. The star begins to shine, its light and heat a beacon in the vast cosmic darkness. This light travels across the universe, reaching distant planets and galaxies, illuminating the night sky. The size of a star, however, plays a crucial role in determining its fate. Larger stars have more mass and therefore more gravity, which affects their life cycle and ultimate destiny. Smaller stars, like our Sun, live relatively long, stable lives. Their hydrogen fuel is consumed slowly, allowing them to shine steadily for billions of years. This slow and steady consumption ensures a prolonged period of stability and warmth. Larger stars, on the other hand, live fast and die young. Their immense gravity accelerates the rate of nuclear fusion, causing them to burn through their fuel much more quickly. This rapid consumption leads to a shorter but more intense life cycle. When these massive stars exhaust their fuel, they often end their lives in spectacular fashion, exploding as supernovae. This explosion scatters elements across the cosmos, seeding future generations of stars and planets. The remnants of these colossal explosions can form neutron stars or even black holes, objects of immense density and gravitational pull. These remnants continue to influence their surroundings, shaping the structure of the universe. The life cycle of a star, from its fiery birth to its dramatic death, is a fundamental process in the cosmos. It drives the evolution of galaxies and the formation of new celestial bodies, perpetuating the cycle of creation and destruction. As we gaze up at the night sky, we are witnessing the ongoing story of these stellar giants. Each star is a testament to the incredible forces at work in the universe, a reminder of the beauty and complexity of the cosmos. The majority of a star's life, about 90%, is spent in a relatively stable state known as the main sequence. During this phase, stars fuse hydrogen into helium in their cores, generating the energy that makes them shine. Our Sun, a middle-aged star, is currently in its main sequence stage. The color of a star during its main sequence reveals its surface temperature and therefore its mass. Hotter, more massive stars appear blue or white, while cooler, less massive stars appear red. Our Sun, a yellow dwarf star, falls somewhere in between. As a star ages on the main sequence, it gradually consumes its hydrogen fuel. This process slowly alters the star's internal structure, causing it to expand slightly and become more luminous. However, this stability is not permanent. Eventually, the star's core will run out of hydrogen, marking the beginning of its end. As a star exhausts the hydrogen in its core, its outward pressure diminishes, unable to counteract the relentless inward pull of gravity. The core contracts, heating up further, while the outer layers of the star expand dramatically, often engulfing any nearby planets. This expansion transforms the star into a red giant, a cool but luminous giant. The Sun, in about 5 billion years, will swell into a red giant, engulfing Mercury, Venus, and possibly even Earth. Inside the core of a red giant, the extreme temperatures and pressures ignite new fusion reactions. Helium, the product of hydrogen fusion, begins to fuse into heavier elements, like carbon and oxygen. This process releases even more energy, temporarily delaying the star's demise. Section 5. The fate of average stars, white dwarfs and black dwarfs. For average-sized stars like our Sun, the red giant phase marks the beginning of their final chapter. As the helium in their core is depleted, they shed their outer layers into space, creating beautiful, expanding shells of gas and dust known as planetary nebulae. At the center of these planetary nebulae, the remaining core of the star, now incredibly dense and hot, becomes a white dwarf. A white dwarf is the remnant of a dead star's core, composed mostly of carbon and oxygen. It shines faintly, radiating away its residual heat over billions of years. Eventually, as a white dwarf cools down over an unimaginable timescale, it will fade into obscurity, becoming a black dwarf, a cold, dense object no longer emitting light. These stellar remnants, scattered throughout the galaxy, serve as silent reminders of the life and death of stars. While average-sized stars end their lives as white dwarfs, massive stars, at least 8 times the mass of our Sun, meet a far more dramatic fate. These stellar giants, living fast and furious lives, exhaust their nuclear fuel much faster than their smaller counterparts. As a massive star runs out of fuel, its core collapses rapidly under its own immense gravity. This collapse triggers a runaway fusion reaction, forging elements heavier than iron, such as gold, silver, and uranium, in a matter of seconds. This catastrophic core collapse releases an unimaginable amount of energy in a cataclysmic explosion known as a supernova. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. Supernovae are not just destructive events, they are also essential for the evolution of the universe. The intense energy released during a supernova explosion disperses the newly formed heavy elements into space. These elements, the building blocks of planets and life itself, enrich the interstellar medium, seeding the formation of future stars and planetary systems. Supernovae also leave behind incredibly dense remnants. If the core of the exploded star is between 1.4 and 3 times the mass of the Sun, it collapses into a neutron star, a city-sized object composed almost entirely of neutrons. Neutron stars are some of the densest objects in the universe, with a teaspoonful of neutron star material weighing billions of tons. If the core of the exploded star is more than 3 times the mass of the Sun, its gravity becomes so strong that nothing, not even light, can escape its grasp. This region of space-time, where gravity reigns supreme, is called a black hole. Black holes are enigmatic objects, their true nature shrouded in mystery. Their immense gravity warps the fabric of space-time, creating a singularity at their center, a point of infinite density and zero volume. Though invisible to telescopes, black holes can be detected by their effects on surrounding matter. As gas and dust spiral into a black hole, they heat up, emitting intense radiation that can be observed across the electromagnetic spectrum. From their humble beginnings in interstellar clouds to their dramatic demise as white dwarfs, supernovae, or black holes, stars play a pivotal role in the cosmos. They illuminate the universe, forge the elements essential for life, and shape the very fabric of spacetime. The next time you gaze upon a starry night, remember that each twinkling point of light represents a distant sun, a testament to the awe-inspiring power and beauty of the cosmos. And don't forget to subscribe to this channel so you won't miss the next episode of Explaining Things in 10 Minutes.